Welcome everyone, my name is Al-Hajabed. For my final project, I'm going to summarize the academic journal, Keeping the Smart Home Private with Smarter IoT Traffic Shaping. Let's get started. In today's world, as most of us probably know, the Internet of Things and smart home devices are currently growing in popularity and availability. A lot of these devices have sensors that 1. Capture users' offline activities in their living spaces, and 2. Send information about those activities to some type of cloud service that is run by device manufacturers, bringing privacy concerns to attention. The concerns are not solely based on the fact that this data is sent to third parties, but also because traffic can disclose private information related to an owner's activities. So this paper is really going to dive into how, even with the broad adoption of transport layer encryption, smart home traffic metadata, really focusing in on traffic volumes, is enough for a network adversary to hypothesize owners' sensitive activities taking place in their own home. The graph that you see, shown in the article, is the traffic activity from a Sense sleep monitor over 12 hours. The traffic spikes on the graph show user activity occurring. The concern is that a user's activities can be hypothesized by a passive network observer from the smart home internet traffic metadata. With this being said, the threat model is divided into 2 classes of adversaries, local and external. Local adversaries are those that can see traffic from within the smart home local area network. Examples could be malicious IoT devices or Wi-Fi eavesdroppers like neighbors or ward drivers. Local adversaries can see MAC addresses, send times, and sizes of Wi-Fi packets. Without access to the WPA2 key, the adversary cannot see any other packet information. But on the other hand, if they do, they can see IP headers and contents of non-encrypted DNS packets. External adversaries can only see the traffic after it has left the home local area network. Examples are ISPs and government intelligence agencies. While they can get the times, sizes, IP headers, and transport layer headers of all packets that leave the smart home gateway router, they cannot see the local Wi-Fi traffic in the home, which means they do not have access to MAC addresses in order to identify devices. With knowledge on the adversaries, there are also some assumptions that are made. As far as restrictions on both adversaries, it is assumed that packet contents are encrypted and inaccessible to the adversary. It is assumed that they can get and evaluate smart home devices, allowing them to watch traffic patterns under various use cases. They can also continuously watch the traffic if it improves activity inferences, but they are not active and do not manipulate traffic to or from the smart home. Next, it is assumed that an adversary has prior knowledge related to the characteristics of different types of home activities, such as when people leave for work or go to bed, which limits the usefulness of the traffic rate analysis. Lastly, related to network delays, it is possible that external adversaries may not see traffic until it has traveled many hops from the home gateway router, maybe due to congestion, which throws off packet timings. As far as the team's experiment setup, they created a laboratory smart home environment with different IoT devices, which you can see the list of devices used in the picture to the right. They next configured a Raspberry Pi Model B as an 802.11n wireless access point. The devices were connected to the Raspberry Pi Wi-Fi network. The rest of the devices were connected to an Android smartphone via Bluetooth that had the applications of the IoT devices. The phone was also connected to the Raspberry Pi network. With this setup, they were able to record all network traffic from the Wi-Fi interface of the Raspberry Pi to and from the smart home devices. Recorded traffic from the Wi-Fi interface of the Raspberry Pi represented a local adversary, and from the wired interface represented an external adversary. In simple terms, the way that a general attack works is that the adversary identifies devices in the smart home and separates traffic metadata by device. The adversary then watches changes in traffic rates to determine the timing of user activities. Most interactions occur at distinct times or over short periods, causing noticeable spikes on bandwidth graphs in between longer periods of no interaction. Such an example is turning on a light bulb. From this information, the adversary infers the types of activities that made the traffic rate seen change. The team found that using traffic rates to make inferences was effective for the devices that they tested, but they only included details on the few shown. On behalf of time and simplicity, I'm also only going to speak about 2 of these, the ones I found most interesting. But the graphs are very informational for all, as you can probably draw conclusions for the ones I do not talk about. For the Amazon Echo, they tested it by asking a series of 3 questions. These questions were, what is the weather, what time is it, and what is the distance to Paris? They asked these questions 3 times, one question every 2 minutes. Figure C shows the SSL traffic rates between the Echo and a single Amazon.com IP address during the experiment. Throughout the experiment, the Echo did send and receive other TCP traffic to different domains, but they were still able to identify the stream that was associated with the questions. An adversary could do the same and use the spikes in traffic to make inferences on user activities. The other device that I'm going to talk about is the Genie light bulb. This light bulb has 2 states, on and off, and these states are seen in network send and receive rates. Figure E shows the light bulb traffic from when the bulb was turned on and off 4 times over a 37-minute period. The activity is shown with the spikes, which indicates when someone turns a light on or off. From this, sleep patterns or home occupancy could be inferred by the adversary. Next, the team evaluated 3 existing defense techniques. These techniques are firewalling traffic, virtual private networks, and independent link padding. Before we get to these techniques, it's important to know the 2 metrics that were used to compare the techniques: adversary confidence and bandwidth overhead. Generally, the ratio of adversary confidence to bandwidth overhead decides the effectiveness of the technique. According to the article, adversary confidence is the expected ratio of correct activity inferences to attempted activity inferences by an adversary with no prior knowledge when traffic rate metadata is defended by a particular technique. Lower adversary confidence means that the technique is more effective at protecting user privacy. Also, according to the article, bandwidth overhead is the ratio of network data sent with and without a given defense technique. A lower bandwidth overhead is preferable because extra traffic contributes to network congestion and can consume user data caps. So now let's talk about the techniques. I included pictures of the exact adversary confidence and bandwidth overhead analysis for your benefit. It is more technical, and I think it is important to see their explanation. There is also a simpler comparison of all 3 techniques at the bottom if you are interested in short and to the point. I encourage you to pause after the initial explanations to read through them. So the first and simplest defense technique is firewalling traffic. The whole idea is to prevent an adversary from collecting network traffic from the beginning. Configuring a firewall to block smart home device traffic would protect devices from user activity interference by external adversaries. Unfortunately, most devices cannot work without internet connection, so taking away wide area network connectivity would leave the device essentially useless. Also, a firewall would not protect against local adversaries' inferences with traffic. The next technique is to have all smart home traffic go through a virtual private network. Quoted from the article, a VPN wraps all traffic from an endpoint in an additional transport layer, aggregating it into a single flow with the source and destination IP addresses of the VPN endpoints. This aggregation could make it difficult to determine which variations in the overall traffic rate observed from outside the VPN correspond to user interactions with individual devices. The team found 3 situations where the effectiveness of a VPN is not good. When one device is connected to VPN, there would be no difference than before. If there are multiple devices that send traffic at different times, time periods with traffic from only one device would still leave room for activity inferences. Lastly, if there is a dominating device, an adversary could make an inference on the activity because it sends the most traffic. The last technique is independent link padding. Independent link padding deals with setting upload and download traffic rates to copy predetermined rates, meaning the adversary would not have information related to device behavior or activities revealed. In the previous slide, you may have seen stochastic traffic padding in the comparison table, so let's talk a little bit about that. The team introduces STP as a traffic shaping algorithm to defend against user activity interference from traffic rate metadata. They described STP in 2 points. The first is that upload and download traffic are shaped evenly, so it is hard for an adversary to tell between the different types of activities for the user. The second is that extra periods of even shaping are injected randomly into the traffic, and an adversary would not be able to tell these periods from real user activity periods. In the paper, they give a really deep analysis of the algorithm, but I'm going to try to sum it up. First, STP chooses a fixed traffic pattern with mean rate R and duration T. STP divides time into 2 discrete periods of length, T. All the activity traffic is padded with a pre-selected traffic pattern. STP also performs traffic padding when there is no user activity, so that the adversary does not know the instance of activity traffic. At the beginning of each period T, STP performs a decision function to determine whether or not to shape traffic during that period. If yes, a start time is selected uniformly at random. Traffic is then shaped to match the fixed traffic pattern. If shaping is already occurring at the start, either due to user activity traffic or padding started during the previous time period, the fixed traffic pattern is simply repeated once the current iteration concludes. Shaping bidirectional traffic, because most smart home devices have bidirectional protocols, brings in two more considerations. One direction may have a higher volume of traffic. Using the same traffic pattern for both directions would be wasteful, so instead STP can use separate fixed traffic patterns with mean rates RU and RD for the upload and download directions, which describes R in the algorithm as for this analysis, R equals RU plus RD to represent the total overhead of STP shaping in both directions. Also, the upload and download traffic locations also need to communicate to synchronized periods of padding since they are in different locations. The article suggests that the best way to implement STP is while also using a VPN so that the traffic is tunneled through the VPN, grouping all smart home traffic onto one stream with one protocol and packet header information not correlated with user behaviors. The team suggested two ways that STP could be implemented. The first deals with Linux-based middle boxes, like a smart home hub, access point, or home gateway router. The team created a service involving a Python script that performs traffic shaping in a custom VPN endpoint. The script decides when to perform periods of constant rate padding for STP. The padding is implemented using the Linux kernel's traffic control system, configured by the TC tool, combined with a user space program that generates cover packets. Using the VPN is similar as to what we talked about earlier. The traffic connects to an open VPN instance, and the VPN endpoints communicate to upload and download traffic, therefore protecting bidirectional protocols. Performing STB on a middle box protects against external adversaries, but not local ones. The second way to implement STB is on devices and servers. The idea is that device developers could include STP as a feature of their devices with custom code or a third-party library. Shaping of upload traffic would occur on devices, and shaping of download traffic would occur on the cloud servers. Performing traffic shaping on devices would protect first hop Wi-Fi traffic, which means local and external adversaries could not make activity inferences. This is awesome because people are probably more concerned with their activity being followed by close-by adversaries like potential burglars or neighbors. As of now, this implementation is less likely because of the extra work for device developers and cloud infrastructure. That concludes my summary on keeping the smart home private with smarter IoT traffic shaping. The journal contains a lot of details, so if you found the summary interesting, I encourage you to check it out because it is pretty cool. A quick Google search will pull it right up. I also included the team's future research suggestions so you can see what may be coming. If you have any questions, feel free to shoot me an email. Thank you.